Wow, pressure is on. Okay. So when my wife was going to ask me, so how was Oklahoma? I'm going to say, warm outside, cold inside. All right, so here we go. Truly, it's an honor to be, well, there's one missing, but that's okay. All right, so it's a true privilege and an honor for me to be here today. Again, I'm going to speak about water quality. I do understand that this actually is also very important in the state, although despite the fact that today's topic is about that every drops count. All right, but, I don't know if we're looking in the future, but for sure, all of us here who've done any water quality monitoring, we all know that, we're doing our best. We go get our water and we analyze it. We bring it back to the lab. We analyze it, and we get so many points for so many stations. And clearly, we're not representing every second of the water quality, and so it's infrequent. But does that really matter? And so I guess the presentation here is there are now new technologies out there to get high-frequency water quality data. But do we really need it? So that's hopefully we'll have a little bit of the answers today. So I just want to tell you that in environmental sciences, we want to tell how the story of how the world works, right? Make hypotheses. We collect data that are inherently partial in time and in space, right? And then from these data, partial data, we infer processes at play, we quantify, we extrapolate, we model, and from all this, we make conclusions on how the world functions and what we should do about it. So I'm just going to give you a little bit of an exercise together. What is partial information? So I'm going to ask you to read this little story. All right, so how many of us here think something bad has happened? You can't cheat. You can't just, you have to come up with an opinion. Who thinks something bad happened? All right, quite a few of us. All right, so actually, I'm going to resample the story, not like the equivalent of our monthly sampling, but a little more. So, who thinks that this is just as bad? Right, so we haven't changed our opinion. So frequency doesn't matter, really. However, had I not come on the first day, or not come the first word, but the third word of the story, we would have gotten that story. So now, how many of you think it's just as bad as they thought it was? Not too many. So all of a sudden, the same story, exact same story that we have sampled partially, either very, very infrequently or a little more frequently. So who thinks now now from this version from the very first, who thinks it's actually not that bad? All right. So half of you have actually totally switched your opinion in about 1 minute, okay? Well, this is the story of what water quality monitoring currently is. We are making decisions from very partial information. And of course, this is a bit of a caricature, obviously. All right, but really, what I wanted to really come up with is that really and oh, by the way, this is the actual little story, I almost forgot. Okay, so now that you've read it, you see that, well, okay, it was not that bad. So now you have the full story, and from the full story, you can make the actual decision whether or not we should do something about, should have gone to the hospital, or, there's nothing really to be worried about, or maybe we should check on Troy tomorrow, or something like this. Okay, so now you have the full story. So you have the full story, so from which you can actually make an informed decision. But when you have only partial information, you make a decision that actually, as we just saw, can switch from totally in 1 minute. Okay? But working with natural waters, it turns out that it's not like in biology where we know that organisms grow through time. Therefore, if we come every month or every other month, we know it's grown in the meantime. You know, what flow, nutrient, and pollutant loads are intrinsically linked to rainfall pattern. I understand there's not much rainfall in the southwest of the state here, but anyway, rainfall is unpredictable. You know, there are no two same rainfall events. So, extrapolating from measurements made during a few rainfall events or throughout the year, regardless of rainfall, is risky. And what I'm going to try to do today is to show you the risk of from infrequent data, and as a result, in my opinion, the need to move elsewhere. Two examples, so an upland watershed and tidal wetland. So if we had continuous water quality data, you know, we have continuous flow, we know how to do that, but if we have continuous water, let's say like nitrate concentration here, like it's actually from Brittany in France. Now from that you can actually do another thing, but had we sampled, so what you see here, you say, wow, for every single flow event there is a dilution effect. Somehow the nitrate concentrations are diluted. What does that mean? There's a lot of information embedded there. But had we not sample continuously, but on a weekly basis, all of a sudden our conclusions are, well, the concentrations do not increase that much during high flow, and you make all sorts of conclusions that maybe not, and if you sample not weekly, but on monthly sample, well, the concentration just doesn't move, come on, it just doesn't change. Okay? So what's the story that our discrete sample is telling us? And I'm just telling you, well, is this really problematic? Well, you just saw that, the chemograph does up and down all the time, and now with just monthly sampling, we just totally erase that information. So, but is that really problematic? All right, let's get an idea. So I'm just going to look at the impact of that on the actual annual nutrient loads. When you have the actual continuous information on flow and concentration, you can actually calculate instantaneous loads, which you can integrate over time, and you can actually draw this, this line of cumulative load, and you can do that at the annual scale, okay? Well, when you don't have continuous, but only the red dots here, well, you have to come up with another method to estimate your load the best you can. So there are many methods out there, one of which is to just calculate a load at each of these points, calculated from instantaneous flow and instantaneous concentration, and average them all out. Do not do that. It's wrong. Another one is to try to get a estimator of the flow-weighted average concentration, which is you add all the loads from each of these points, and you weight them by dividing them by the summation of the flow. So that gives you actually a flow weight, an estimator of the flow-weighted concentration. Is the least bad method, it seems. Okay. And it turns out that there are lots of methods out there. I'm obviously not going to go through them, all right? But another thing that I want to just to show you is that, in fact, there's not one error. There's an infinite number of errors possible. So when we try to quantify the uncertainties on these measurements, on these induced by infrequent measurements, I just want to just give you bring a little awareness. This again, if you go back to the actual, if you were to have the continuous data and you were to go on a weekly basis on Monday mornings, you might have gotten this chemograph in green here. Can you see the green? Not really, kinda. But had you gone not on Mondays, but on Thursdays, but still every week, you might have gone this one, right? In reality, between Monday and Thursday, there's an infinite number of possibilities for you to go sampling, right? So in the end, in the first case, you might have made this error. In the second case, you might have made this error. But overall, you can really have a theoretical infinite number of errors, but the beauty of this is that you can actually statistically characterize the distribution of the error, all right? So this is what this histogram is showing. It's just showing essentially that you're not making an error, but you're making a distribution of error, and in really between the two dashed lines vertical, the left and the right one, you have 90% of the total errors that you're going to make. Okay, so in this case, we're saying that for this particular sampling frequency, and it was for, I think, nitrate on that particular watershed, we were going to make an error very small of minus 1.5 to almost 3%. Well, that's nothing. Come on. True. All right, so now I'm going to take the same graph. That's like this. I'm going to put it on its side, okay? And I'm going to show this is the same graph. So now I have represented these histograms for 30-day sampling, so monthly, 21-day sampling every 3 weeks, 14, 7 days, so weekly sampling, and so on. And you see that for monthly sampling in that particular watershed, we would have made an error on the actual annual load by between minus 20 and plus 20%. Well, if you're trying to do some BMPs in your watershed and say, and you know that you're going to enroll maybe 5 to 10% of the land of the landowners, well, if you're trying to measure the effect of that BMP by plus or minus 20%, well, chances that you're going to see it are essentially zero. So it's a bit like as if I was trying to measure the distance between me and the back wall here with a Mars telescope. It's just the wrong instrument, right? Well, I know you guys are more interested in phosphorus. When I look at phosphorus in the same watershed, for monthly sampling, we're between minus 50 and plus 60% error. So think about it. And if we take not monthly samplings, oh, come on, it's monthly sampling. We can do better than that. All right, now let's look at weekly sampling. For 7-day sampling, we still would make a minus 30 and plus 30% error. So we're making a lot of, all of you here who've done water quality monitoring and gone out there and brought the, when it's cold, wet, and everything, go back and say, we're doing all this, and we're still measuring plus or minus 5% in the lab, but you're telling us that my load is plus or minus 30%? Is it really worth it? Or maybe 50 or 60%? All right, so obviously all this depends on the watershed, it depends on the parameter, it depends on many things, and we have published quite a few papers, so I'd be happy to talk about you in details about this later, but of course I don't have time to go into the details. But there are techniques to actually evaluate globally what the bad uncertainty of each constituent is. So there is no hope? Yes, but hold on. First, I'm going to want to show you some really cool stuff about tidal wetlands, because this is kind of the caricature of how dynamic a system can be. All right, so we're in North Carolina, second longest linear length of tidal shore after Louisiana in the nation. And I'm going to zoom right here in the, if I can get, yes, right here. And I'm sure you guys have heard about, the Mississippi River, Mississippi dead zone and all this. Well, we have the largest privately owned farm that's producing extremely productive farm, not because they put a lot of fertilizer necessarily, but because the soils are just fantastic. Well, they're not hundreds or thousands of miles away from the dead zone. We're right there on the very, very close sensitive estuaries. Okay. So the problem is, can we do something about this? And my colleagues took, and as a result, unfortunately, we have some shellfish problems. And so my colleagues, Dr. Mike Birchall and Dr. Robert Evans, said, well, maybe we can actually, between the agricultural production area and the estuary, maybe we should restore a marsh here where we can actually divert some of the marsh drainage water, and maybe we can clean up the marsh. And I think that was a good idea. This is how the marsh looked like. It actually looks like almost a pristine marsh nowadays. But just to give you an idea how things are varying over there, it's tidal, so the flow actually goes both directions. So you see actually arrows here that give you the direction of the flow, and the size of the arrow gives you the magnitude of the flow. So each data is every 15 minutes, and you see how quickly things change. Of course, you say, well, we don't have this in Oklahoma. Yes, you don't. I agree. But at the same time, this is just to show you that systems out there are really extremely dynamic. And another reason I want to show you this is because the effect of infrequent sampling are fantastically magnified. So this was just for the water flow. So now if I give you actually the concentration variation. So in gray, I think you can see, in gray you still have the same hydrographs rather. And on the right side, you'll have, in the map here, you still have the arrow which size will change with the direction and magnitude of flow. Now the color, I don't know if you can see very well, but the color of the arrow is going to change. And it's going to change following the chemograph that's in red here. I just want you to have, the reason why I'm really insisting on showing this is because I just want you to have an idea how quickly things change out there in the environment. So see how the arrow, the size of the arrow changes, but you see the color of the arrow is just changing rapidly. We have a little peak there, boom, boom, it goes down, up and down, up, down, and so on and so forth. And so all this, and at the beginning we said, oh, come on, this is just a joke. I mean, our instruments are just not working. And it turns out that when we go back, we can go at every single peak or trough, and it actually makes sense. There is something we can explain every single one of them. It's not a measurement error. So what are the impacts of this? Well, so we tried to measure how effective our marsh was. What we did, we said we did a mass balance. So not only a water balance, but also a mass balance. So we measured how much nitrate came in and came out. And so we did that over essentially 14 months. So I'm just going to show you 10 days, not even that. So this is the hydrograph. So you have positive and negative values because, again, flow can go both ways. It's a tidal wetland. And this is the chemograph that goes with just for nitrate. Okay? And when you actually do that at both the upstream and the downstream station, you can actually see whether or not the global balance is positive or negative. Positive means here it's actually there's more nitrate that came in than left. So in other words, our marsh has actually retained nitrate. Yes, that's what we wanted. All right, great. Well, and then people said, well, I could have told you that before. And well, the problem is that we could have, yes, and that's what we thought. But the magnitude was the key. By how much? And so had we not sampled every 15 minutes like we did with our instruments I'm about to talk to you about, and we would have maybe just taken that just every 6 hours. You know, we're not talking about days here. We're talking about 6 hours, not 15 minutes, 6 hours. Maybe we would have seen this beautiful chemograph in red here. And you know what? Some of us would have said, possibly myself, look, the tides do not matter. The nitrate concentration goes up and down and up and down and up and on a daily value. We found something fantastic, guys. The tides do not matter. The concentrations just vary on a dial basis. That's what it is. That's a fantastic new knowledge. Well, no, as you see the gray in the background, really has nothing to do with that, okay? But our partial data, we've got to come up with ideas on how things are working. And, you know, maybe not sampling starting 6 hours at 1 in the morning, but maybe at 2 in the morning, we would have gotten a totally different chemograph, right, as you can see here. And I can go on and go on and go on, and maybe you would have gotten this one over here again. And in the end, if you do lots of them, you see that in reality, again, you know, you try to see the statistical distribution of all the errors you might have gotten. You find that you can find lots of things. And so when we did that exercise for nitrate or for dissolved organic carbon, we see that, you know, even for carbon, we would have said that in many cases we would have had a release of carbon. In many cases, we would have had lots of carbon retained. Oh yeah, we're sequestrating carbon, it's fantastic. The marshes are sequestrating carbon, this is great. Well, it turns out that the actual thing for 10 days says it's pretty much carbon neutral over 10 days. And so we could have, you know, sampling infrequently, we would have changed our conclusions. We could have made wrong conclusions about the nitrate dynamics in the marsh. No, there's no dial variation. There's a lot more variations than that. So that would have been a wrong hypothesis. We would have possibly under or overestimated by 70 or 100%, 130%. Okay? So in other words, we could have just thrown a coin and would have been just the same probability to be just as good, right? And the worst part is that we would have never known about it. Never, never, never. It's really scary, right? You know, you try your best, and all of us here, there's not one person that can say, "Oh, I tried my worst," and you know, no wonder. No, everybody's trying to his best, right, or her best, right? All right. So I believe that infrequent data prevents from understanding processes at play. There's no doubt about that. You just cannot catch the stochastic nature of hydrological processes. Most of the phosphorus that's coming into Oklahoma lakes, although I haven't seen any of the data, but I can bet that most of it occurs in very little percent of the time. Probably 10 to 20% of the time, you might have 60 to 80% of your total phosphorus load coming into your lakes. So if you miss these 10 or 20%, you miss the whole story. But the problem is that you don't know when it's going to happen, because it's all linked to the rainfall. And it really, infrequent data, induce high risks of making the wrong assessment, and as a result make uninformed decision, or not enough informed decision. So I promised there was some hope. All right, let's look at it. So we tried our chance. When I was in France, we were contacted by these Austrian manufacturer who just came up with this UV visible spectrophotometer that have been available for a long time in labs, but they decided to actually make them field ready. So we have actually installed them. We've solved their own little dirty little secrets. And how does that work? Well, you actually send a light, and it goes through a concentration, and some of the light is absorbed, and that absorption depends on the path length and the concentration. So as a result, you get absorption spectra, and you see that in high nitrate, the spectrum looks a little bit different than the low one. All right, well, of course, you know, I don't know how to say, oh, clearly this is 10.4 the high and 3.2. So clearly we need to come up with statistical techniques to extract the information we're looking for. I mean, the manufacturers tell us, well, yes, you know what, nitrate is absorbed in about the UV range, and the carbon organic, dissolved organic carbon about also the UV range, but a little further towards the red, and turbidity, we can measure it in the visible range. All right, so well, we said, okay, great, well, we'll buy these because it's still going to be better than not having that. And so most manufacturers advertise for just nitrate. I'm sure you've heard about the Suna in the US. Some add DOC and turbidity just like the SCAN does from Austria. But really, right at the beginning, we said, well, but you know what? Other parameters are linked to turbidity. We know total phosphorus is linked to turbidity. If this instrument can do turbidity, maybe we actually can do or assess total phosphorus. And maybe, you know, since it can do DOC, maybe we can do dissolved organic nitrogen, because we know that, in fact, a lot of the loads is actually not only in the inorganic form, but also in the organic forms. Okay. So the question that we had right away, could there be some covariability between light absorbance and other parameters? All right. So we obviously asked the manufacturers, can you give us your code, please? And they said, well, we'd love to, but we just can't. And I'm glad they didn't, because so that forced us to actually go back and say, all right, well, I mean, it can't be that complicated, come on. And so we went in there, and they've created the manufacturers did things the right way. They essentially, we've built an algorithm that will work from water from Oklahoma, North Carolina, China, France, South America. Everywhere it will work. And we can guarantee that it will work for nitrate. And so that's what they advertise for. And provided that you do some local calibration. They had to come up with algorithms that had to be affordable, and that the small computer on this probe that's about this long and about 5 centimeters in diameter could do. So we then used chemometrics. We invested into chemometrics. It's a technical, I'm not going to go there, to create regression between absorbance and concentrations. And we use this tool, which is called partial least square regression. And I'm not going to go through it. All I can tell you is that what it does is that it allows to do some really, really nice correlation. This is for the correlation that we have for nitrate in our lab, in our marsh. We have that for, TKN, organic nitrogen. Never advertised for it. We have a very acceptable correlation. DOC, we didn't think that was going to work in a brackish environment. It worked. How about TSS? Well, yes, it works. TP, I know some of you are interested here. TP, we can do a very good job with TP. Phosphate. There's no reason whatsoever why phosphate should absorb any light. So this is now, so at the beginning we say, well, what's this? So what we think is going on is that there are light-absorbing constituents in the water. They are co-varying with phosphate. So if you're able to actually create a local calibration, you're the king. Because all of a sudden you just can measure this phosphate concentration on a continuous basis. You want more? This is from Brittany. We've done for nitrate, DOCD, silica. I just did a study with some colleagues at Virginia Tech. We've been able to make correlations with, I want to say, 21 parameters, including titanium. Okay. So what we're proposing is that we're really proposing to do water quality rating curves, just like we've been doing for stream water, flow. Every single station has a rating curve, as you all know. Sometimes we use equations, but it's always better to actually make sure the equation works, okay? So we're just proposing to do water quality rating curves, where we have an instrument that gives us a signal from which we can extract, as long as we can correlate and create a regression locally, we can actually get something, okay? So there's lots of work. There's hope. There's one answer, for sure. Certainly, we do not have the answer. There's no doubt about that. So many things are remaining still unknown, and we're working on this, actually. How many samples do we need to create these water quality rating curves? Because if we need 50, well, are we getting a whole lot, really? Yes, we are, but it's not going to be cheaper. Can we actually, this is going to be cheaper or more expensive? Yeah. So now going back to the initial question, continuous water quality, is it really necessary? To me, in my opinion, it's the only mean to capture stochastic events which are intrinsically linked to hydrological processes. This is the curse of our science, and we are down to stochastic events. We cannot do we cannot apply the standards and methods that have been developed in biology and in immunology for decades, and for which we're just inheriting this. I mean, in biology, they have the luxury of knowing that things are going to grow. They're not going to go back down to nothing and grow back. Although chlorophyll can change very, very quickly in a lake. That's very different. But anyway, it's the only mean to capture the effect of biogeochemical processes that we've never seen before. I mean, this Virginia Tech lake, we're seeing some very, very intriguing things that we have still no idea how to interpret right now. It's clearly the key to improve or revise our models. Remember, all the water quality models that all of us here, including myself first, are using are based on infrequent data. They are just dots. And our models are predicting a nice continuous data series. Maybe all what we're doing is just right, or maybe not. It's the key to improve our assessments and make better decisions. So my opinion, are they necessary? Absolutely. There's no way around it. Well, unfortunately, there are some uncomfortable questions that come with it. Should we keep monitoring stations that have 2, 6, or 12 samples per year? I don't have the answer to that. I think maybe we should, and for what water quality parameter, we should certainly start thinking whether or not we want to have some stations for which we intensively monitor, where we know the uncertainty is this, very small. And maybe rather than, do we want 5 stations where we know the uncertainty, or 100 where the uncertainty means like trying to measure the distance between here and and the wall with the Marsh telescope. It's uncomfortable. I don't have the answer. Or is there a right compromise? Because there's no doubt that for several years, not to say decades, we're going to keep monitoring infrequently to many stations. There's no way around it. So I think we have actually come up with methods to actually predict these uncertainties enough that might actually give an opportunity to really look at that very interestingly and very in depth. So I encourage the water boards and other agencies to actually really want to look at these uncertainties and come up with essentially, shoot, I forgot the English word. Any charts, water quality charts or uncertainty charts. Are our monitoring standards obsolete? You know, the EPA standards that we have to sample two or three replicates. Go back to the lab, they also have to do 1 or 2 replicates in the lab. Well, in fact, with Dr. Munoz Carpena, a colleague and friend of ours at the University of Florida, we're just trying to apportion where the uncertainty and the global uncertainty, how much comes from the lab error, how much comes from the infrequent measurements, how much comes from the flow, and lab error is not a big factor. You can actually have a pretty bad error and still it's not going to make a whole lot of difference on the overall uncertainty. I know for us chemists it's like, oh, don't say this. Come on, how do you dare? But anyway, so just imagine for a minute that we would have cell phone apps on the Maisonette app where we would have each farmer could check the water quality now and for the last day of the month. Do you think he or she would say, when he or she sees that X% of the fertilizer I just put are actually in the water, you think he or she would say, this is perfectly great? You know, as soon as I started doing a family budget at home, trust me, we reduced stuff at some areas. As soon as, you know, if each homeowner were to look at the quality of the neighborhood creek, do you think he or she would put as much of this on his or her lawn or pot? Certainly not. Right? So, because I think the more informed we are, the better our decisions. We do better planning, and we do a lot much less wasting. So, we need to come up with sensors that bring the ability to everyone to actually have, you know, their own data. Because as soon as we have their own data, so we need to democratize a lot of our sensors out there. We're not there yet, but there's no doubt this is where we need to go. So we started to do that ourselves. We started to make a system that can measure water levels with using images and webcams. Because as soon as you have an image, you know, you don't need to actually understand what all these ups and downs means. When you have an image or a video that feeds what's just happened, everybody understands. Everyone. And there are lots of things. So we actually created this little startup company, KHCAM. I have a video, but it's not there, so it's not going to work. All right. So the challenges, though. A lot more information so far with the technology that we've been tested comes with a lot more work. I'm hoping that in 10 years it's going to be a lot less, but right now it's a lot more work. Okay? And right now it's a lot more money. There's no doubt about it. But I know that all these state and federal agencies know that they want to do this, and I'm glad we're all moving in that direction. Because I don't think, in fact, I doubt we have the choice not to invest in these systems. We just don't have the choice. We're going to have to do that, all of us. At small scale at the beginning, there's no doubt about that, but if we don't do that, we just partial story halt progress. If we don't do that, we're going to be stuck where we are, and no one wants to do that. Everyone wants to go and look in the future. So I thank you for your attention. I'd like to try to entertain some of your questions. Thank you.
We have time for questions, so we can take 1 or 2 questions. Somebody asked me, why are you smiling so much? You're in reference wall. The governor walks in, next to me, and he goes, are they going to stand up when I start talking?
Excellent question. So as a result, as you very well pointed out, the rating curve is only valid if you somehow manage to reach throughout the range. So, well, that's why it's not cheap, and it's going to take some effort. It's just like for when you're trying to do a water quality flow rating curve. You have to do your best to capture that high flow event. Somebody's going to have to go up there and just do the manual measurements very quickly to get that extra point, without which your water quality, your flow rating curve is wrong. So it's going to be the same thing. So it's possible that the persons that do the flow rating curves might actually take a sample at the same time, because it turns out a lot of the high concentrations are going to be at the same time. But it's really going to have to, there are lots of, it's a very good question. We're going to have to come up with strategies to make sure we sample enough of the time to get these high values. So one way is to actually look at to actually systematically sample water with an automatic sampler, and look at the actual automatic reading. And if the automatic reading seems to be really high, then take the samples that might be promising to expand the water quality rating curve. So it's not simple. I'm not saying it's simple right now, but it's certainly one way to start looking in the future. It's a very good question. Thank you. Yes, sir. It's a great question too. So the question was about, there are passive samplers that we think are integrating over time whatever comes through. I haven't looked at that, but really we should. We should have some passive samplers out there in our stations where we're monitoring on a continuous basis and try to see how much they correlate. We haven't done this. It's a sin, because we have all the means to do that. I just don't know. I don't have these samplers. If you have some and you want to give me some, I'll put them out there and I'll send them back to you. But seriously, it's a great question.